Math, time, speed and distance.
Chapter 11. Time, Speed and Distance. Concept Notes. Physical bodies can be either stationary or in motion. In motion, the body can either move at constant speed or variable speed. The most basic of the relationship between time, speed and distance is equal to speed into time taken. The units have to be consistent in this relationship. Relative speed. Relative speed is a phenomenon that we observe every day. Suppose you are traveling in a train and there is a second train coming in the opposite direction on the parallel track. It seems that the second train is moving much faster than actual. If both the trains are moving in the same direction on parallel tracks at same speeds, they seem to be stationary if seen from one of these trains, even though they might actually be at speed of 100 km per hour. So what you actually observe is your speed relative to the other. If two objects are moving in opposite directions towards each other or away from each other on a straight line at speeds u and v, then they seem to be moving towards each other or away from each other at a relative speed is equal to speed of the first plus speed of the second is equal to u plus v. This is also the speed at which they are moving towards each other or the speed at which they are moving away from each other. If two men move in the same direction with speeds u and v, then relative speed is equal to difference of their speeds is equal to u minus v. This is also the speed at which the faster person is either drawing closer to the slower person or moving away from the slower person, as the case may be. Downstream and upstream motion. Downstream motion of a boat is its motion in the same direction as the flow of the river. Upstream motion is exactly the opposite. There are two travel parameters in these problems. Speed of the river. This is the speed with which the river flows. Speed of the boat in still water. If the river is still, this is the speed at which the boat would be moving. The effective speed of a boat upstream, b minus r. The effective speed of a boat downstream, b plus r. Circular motion. Problems in circular motion make use of both the relative speed and the LCM concepts. Clocks. Clocks follow the principle of relative speed. Take the instance of a typical clock. There are two hands in the clock, the hour hand, the minute hand. Both are moving in the same direction. The hour hand moves half degree per minute, whereas the minute hand moves 6 degrees per minute. The minute hand is constantly chasing the hour hand. The relative speed of the minute hand with respect to the hour hand is 5.5 degrees. The types of questions that you would encounter would be: time and work. Time and work problems are similar to the time, speed, distance problems. The speed is in terms of the rate of doing the work. Distance is in rates of the quantity of work done, and the time is the time taken to complete the job. Pipes and cisterns. What comes as pipes problem is very similar to the problems of time and work involving the two people, where one was demolishing the wall. The only difference is that in pipes and cisterns problems, we have an inlet pipe that is doing positive work, and there is an outlet pipe that is doing the negative work.
Algebra.
Chapter 12. Algebra. Concept notes. The most fundamental expression in algebra are what are called as monomial. An expression having only one term is called a monomial. Example: x, y, 2xy, 3xyz, etc. The number of variables is immaterial. For instance, the number of variables in the examples varies from 1 to 3. Monomials are the building blocks for any algebraic expression. The constant that appears in any term other than the variables is called the coefficient. Binomial. An expression having two terms, two being either a plus or a minus. Example, x plus y, 2x minus y, x3 y square plus 3xy, etc. Polynomial. An expression having two or more than two terms, x plus y, 5z, 2x square plus 4yz cube plus 3xz square, etc. Functions. A function is an operation on a variable establishing a relationship with another. The operator transforms the variable into a unique value. Example, if an operator transforms any variable x into another value equal to 2x, the representation for this operation is given by fx is equal to 2x. The resultant value is normally denoted by y. So, y is equal to fx is equal to 2x. The standard notation for expressing a function if f is to x is equal to y, the interpretation for this representation is that any value x from set x is mapped onto a unique value y in set y. The operator is f. For example, if fx is equal to y is equal to x cube, this implies that for any real value of x, the value it is mapped onto, y is equal to x cube. So if the value of x is 2, then the value of y is equal to 8. If fx is equal to x to the power of 4 plus x square plus 2, what is the value of f2 and f minus 2? Solution. The value of y would be 2 to the power of 4 plus 2 square plus 2 is equal to 22, when the value of x is equal to 2. Observe that the value of y could be the same for two different values of x, plus 2 and minus 2. But for any one value of x, the value of y is unique. Such functions which have the small value for both fx and f minus x are called even functions. A function need not be in just one variable. It could be in any numbers of variables. For example, there could be a function fxy is equal to z is equal to x square y plus y square x is equal to xy x plus y. This is a function in two variables. If you notice, all the polynomials, binomials and monomials are different kinds of functions. Arithmetic operations on algebraic functions. Let us look at the arithmetic operations on the algebraic expressions with reference to the form of the resultant expression, degree of the resultant expression. Remainder or factor theorem. This theorem states that if a function fx is divided by x minus a, then the remainder would be 0 if fa is equal to 0. In other words, x minus a is a factor of fx if fa is equal to 0. Then a is called a root of the expression fx. In general, roots are the values of the variables when the expression equals 0. In case fa is not equal to 0 but is equal to a constant c, then it means that fx when divided by x minus a leaves a remainder equal to c. Simultaneous equations. An equation is a relationship of equality between algebraic expression and a constant or another algebraic expression. Alternate approach. If all these points are represented as coordinates on a graph and joined together, they form a straight line. The graph would look like shown here. The interpretation of equations as graph comes under the purview of coordinate geometry. Any linear equation in two variables can be represented as a straight line on a graph with the x and y as the dimensional axis. On the contrary, an equation on a system of equations having a unique solution have only one set of the variables that satisfy the equation. An equation or a system of equations have a unique solution if and only if the number of variables is equal to or less than the number of independent and consistent equations. To understand better, let us examine the terms. Independent. An equation is not independent if it is derived as a combination of any of the other equations in the system of equations. For example, suppose there are three equations x plus y is equal to 4, 2x plus 3y is equal to 5, 4x plus 5y is equal to 13. The equation is not independent of the other two, since it can be formed by 2i plus 2. Inconsistent. Consider the two equations. X plus y is equal to 4. 2x plus 2y is equal to 7, or x plus y is equal to 3.5. The second equation established a different relationship between x and y as compared to the first equation. So they are said to be inconsistent. Such a set of two equations does not have any solution. An example illustrating a system of simultaneous equations does not have any solution. An example illustrating a system of simultaneous equations having a unique solution. If you solve these equations, we get the value of x is equal to 0 and y is equal to 2. In graphical representation, each of these equations represents a straight line. The point 0, 2 lies on both of these two straight lines, which means it must be the point of intersection of these two straight lines on the graph. Quadratic equation. A standard quadratic equation is of the form ax squared plus bx plus c is equal to 0. An expression is a single variable of degree 2, has at most two roots. So, when solving any quadratic equation, we are identifying the values of x for which the expression becomes 0. So the solution to a quadratic equation is equivalent to finding the roots of the expression. The roots of the quadratic equation could be real and different, real and equal, imaginary. The value b squared minus 4ac is called the discriminant and is denoted by d. Quadratic inequalities. X squared minus 7x plus 12 is greater than 0 is equal to x minus 3 into x minus 4 is greater than 0. To solve this quadratic inequality, we have to find the range of values of x, for which this relationship would be valid. Using this simple numerical logic, we can state that in order that this condition is satisfied, the following has to be true. Both x minus 3 as well as x minus 4 have to be positive, or both x minus 3 as well as x minus 4 have to be negative. If both x minus 3 and x minus 4 are positive, then x must be greater than 4, and if both x minus 3 and x minus 4 are negative, then x has to be less than 3. For all other values of x, the expression x squared minus 7x plus 12 would be either less than or equal to 0. So for values of x lying between 3 and 4, x squared minus 7x plus 12 would be lesser than 0.